just like, you say something like that, I'm like, what? And you're like, just never mind. You know, I want
yeah,
to
you can write the email if you want.
Sending the other way.
She can get email from anyone. We're typing email.
All right, kids, let's rock and roll here, guys. Last section, guys, in 3.9, we're going to start looking at modeling of polynomial functions. And I'm going to be really honest with you. Desmos is going to be a nice tool to use with this as we progress. So in 3.9, modeling with polynomial functions, how about a volunteer to read my essential question? Who wants this one? Who's reading that for me?
I will.
Go ahead, Sam.
How can you find a polynomial model for real life data?
Okay, so we're looking to say, here's some real life data, and we want to come up with a polynomial model for this. Now, coming up with that would be kind of difficult to do, and Desmos is going to help us with that. You guys remember when we were doing quadratics, we said type your table in and then do like the y1 is, remember the little squiggly mark we put in there? And then like ax1 squared plus bx1 plus c. Kind of going to do the same thing again today. And I think you're going to be like, whoa, that's pretty cool. That's going to be helpful as we progress through things. So definitely going to want Desmos open there when we get to that. So guys, goals for the day then to answer that question, how do you find a polynomial model for a real life data? First of all, we need to know how to write polynomial functions for sets of points. We're going to write polynomial functions using what we call finite differences. I'll show you what that means. And then the technology we're really using to find models for data sets is going to be Desmos. Okay. Couple of vocab terms. First one that I have there is what, kids? Called finite what? Finite differences. Okay, let me squeeze this in here quickly. So we'll get a definition in here. Finite differences. Okay, finite differences occur when, whoops, okay, here's the deal. It says when, gosh dang it, where are my tools? When x values are equally spaced says the difference of consecutive y values is what we're after. Okay, so this here says when x values are equally spaced, it's the difference of consecutive y values that we're looking at. So get that down first, and I'll show you what this means. It says when x values are equally spaced, it's the difference of y values. So what does this mean right here? Okay, what does this mean? Well, what it means, kids, is this. If I had an XY table like so, maybe my x's are up here and my y's are down here. Okay, so kids, what do you think the next x value in this table would be? 7. Why 7? Okay. So in order to look at what we call finite differences, we have to understand that the spacing between the given x values is always the same. So the x value always jumps up by how much each time? So the first question I'm going to ask about finite differences in this section is, hey, are my x values equally spaced? In other words, are they jumping up by the same amount from one term to the next? Okay, in this case, they jump up by 2 each time, right? Okay. So then we would talk about the finite difference. Maybe y is 12. and then maybe 9, and then 6, and then 3. We would say the finite difference right here is 12 minus 9, which is what? 3. And then the 9 minus 6 would be the next one. And then for this jump of 2, you had a difference of, again, 3. So we're saying for this jump of 2 in x, there's a change in y of 3. So a finite difference is going to be the difference in y values, consecutive y values, when the x jumps up by the same amount. And we'll look at an example like that, okay? And then scatter plots. You guys know what scatter plots are. They're just a collection of data points in a collection of data in a graph. Kind of looks like this. Have an XY plane. You might have points just scattered all about here like so. Okay? It's just a collection of data in a coordinate plane. That's all it is. I love these types of problems. This is so cool. Okay? We're going to start modeling data. We have to start writing an equation for this graph right here, kids. Okay? Never mind this up here, all right? Never mind this up here. Just forget that's even up there, okay? You okay with that? All right. This is write a cubic function whose graph is shown up here. First of all, kids, we need to understand what the general form of a function is. So I'm going to write this down, okay? General form of these right here, first of all, I'm just going to give you some rules, okay? To write a function for this graph that's shown, the first rule you want to do is always look at your zeros. Okay. How many zeros does this graph have? 3 of them. There's 3 of them, okay? Where are my zeros at, kids? -3, 1, and 2. Okay, so here's the deal. To write a function for this, I can just jump right into this and make this very simple for you, or I can give you all the terminology and notation that comes with it and try to confuse you. Make it easy?
Yeah.
Okay. If I had to write a function for this, this is what I would do. Okay. What's going to be new for us today is this. We have to be exact. And I'll show you what being exact means here. Okay. Your function for this, how many roots again here, kids? 3 is going to take on the following form. You're going to have a form y equals. All right. I'm going to put this letter in red, and I'll tell you about that letter here in a second. All right. Kids, I'm going to have down the form here, y is going to equal k. K representing some number. I don't know what that number k is out front. I don't care what it is for now. Well, what I put behind k is x minus a, x minus b, x minus c. How come I didn't do an x minus d here? Anybody have a thought? There's only 3 zeros, so I only have to do 3 sets of parentheses. So let's plug our zeros in here. I would have y equals some constant of k. Whoops. All right, here we go. X minus the first. What's the first one right here, kids? -3. But subtracting -3 really turns that into what, kids? X plus 3, doesn't it? And then x minus my next one, kids. X minus 1 times what? I want to put something here. All right, no problem. The situation now is this. We've got y in terms of x right here, or if we called y f of x in terms of x, we could have that too. But we've got to figure out a value for k. All right? And how you find your value for k is to see if there's a point not on the x-axis. Is there any other value in this graph that's not on the x-axis? What? Where's 6? Oh my gosh, kids. Here's this point right up here, okay? This point right up here, I understand that's a y-intercept of 6, but coordinate-wise, that would be what, comma, what? Okay, here's the deal. We know that we have the function y is equal to k times this mess right here, because everything in black represents where our zeros would fall, okay? So what I do then is this. Now we're going to use a point not on the x-axis, and that point is 0, comma 6, which states that when my x value is 0, the y value is what? Okay, we can use that information, kids, to help us figure out what the k value would be. They're basically going to say, hey, why don't you plug that point in for x and y? So knowing that this point, not on the x-axis, is part of this polynomial graph right here, what would you plug in for y given this point not on the x-axis? All right, and then you're going to have 0 plus 3, right, kids? Which is what? Because I'm plugging 0 in for x and 6 in for y. What is 0 plus 3, kids? What's 0 minus 1? What's 0 minus 2? All right, you help me with the math here. I'm not very good at it, but what's 3 times negative 1? Negative 3 times negative 2 is? So from this, we obtain that 6 on the left is equal to 6 times which variable, kids? Kids, if that's true, after I plug in 0, comma 6, what's that make the k value there? 6 is equal to 6k. K is 1, right? Okay, so my final function here becomes the following. Simply becomes, ooh, purple's nice, y equals, what's going in for k now, kids? 1 times x plus 3. I have a question. You want me to make you multiply this all the way out, or you want to leave it in this form? I say leave it too. There it is, right down here. Okay. What was the first thing we looked at, kids? Zeros. We're going to put it into form y equals, all this stuff in black is my zeros, but what do I have to throw out in front, kid? Some value k. K is a constant. It might be multiplied by 3, 9, 12. In this case, we were multiplying by 1 because we had to plug in which point? Had to plug in 0, comma 6. And we had to plug 0, comma 6 in because that was the one point that was not where? It was not on the x-axis. There's your function right there. You know what? If I would go into decimals and type this in, guess what graph it's going to give me now? Exactly that. Okay? Exactly that. All right. Well, what if we run into a situation like, everybody have what they need here? Then this situation. Oh my goodness gracious. Oh no! What's that? Why put it up there twice?
Because it's like, if it hits the line,
Okay.
it doesn't go on.
Yeah, so polynomial functions right here, kids. This is important right here. If a graph comes down, touches the x-axis, and takes off, or this just touches the x-axis, you have to account for that 0. You have to account for that 2 times. Okay? Now I'm going to show you something else quickly. You might want to jot this down maybe on the very back side or the blank side of your notes. Sometimes you'll have graphs that do this. They'll come up, they'll flatten out right here, they'll get really flat right there, and then they'll take off this way again. Right here, this is a unique situation too. It comes in here, flattens out right there, flattens out right there. This one here you would actually have to account for, not twice, but anybody want to guess? 3 times. This is considered a triple root, like this. So if it comes up and it really flattens out right there like that, and then heads back this way, and I think you'll catch it. I don't think there's any questions like that in the assignment. But just on a side note, you would have to account for that one 3 times. So, here's the deal. Let's just talk about degrees right here. How many turning points does this graph have? 2. So it's got to be at least a degree 3 function. Well, I only have 2 roots up there. So when it comes down and just touches like this, kids, this gets accounted for twice. If it touches the x-axis and then takes off and stays on the same side, in other words, if a turning point is ever on the x-axis, you account for that twice. So here's how this looks. To write a function for this, we're going to say y equals some constant k times. Help me with the zeros, kids. What's this first 0? -1. So we're going to call this x plus 1. And then what's the next 0? But here's the deal. We're accounting for this how many times? So this would be like x minus 2 times x minus 2, or if you will, x minus 2 to what power? There it is. Okay. Now, is there a point that you definitely know that is not on the x-axis that we could use to plug in for x and y so that we can find that constant out front? 0, comma. Okay, so let's use 0, comma 4, which states that when my x value is 0, the y value is 4. Roll, kids. What's going in for y? 4 equals some constant k times. Here we go. What's going in for x? 0 plus 1 is what? Okay. 0 minus 2 is what? -2, isn't it? What's -2 squared, kids? Oh my gosh. What's 4 times 1? Okay, what do we get for a k value again? Okay, so we have 4 is equal to 4k, which means k is 1. So my final solution is simply y equals the k value of 1 times x plus 1 times x minus 2 squared. There it is. Was that so 2016 or 17? What's 2018 right now? What do you guys do in 2018? Bottle flip was 2016, wasn't it? Or was that 2015? That's pretty savage. You guys are... Wait, that was 2 years ago also, wasn't it? What's that thing?
The light up one.
Fidget spinner,
Wasn't
yeah.
that like 2016?
That was fun. I know.
The boys had it.
Oh yeah, that was.
Core concept right here, pretty important right here, kids. I like this type of stuff, okay? We're going to use this type of stuff to finish up our notes. This is not going to take very long today, all right? Example 2 says writing a function using what? Finite differences, okay? It says use finite differences to determine the what here, kids? The degree of the polynomial function that fits the data. Then use what? Okay, here's the piece that I'm after, okay? First of all, I forgot to put y down here in this box. So do that for me right there, kids. Put a y in there. Okay, here's what they mean about finite differences, kids. First of all, take a look at my x values. Can I even consider finite differences right here? Look at all my x values in this, kids. Are the x values changing by the same amount each time? Do I have the same distance between each x from one to the next?
Yes.
Yeah, they jump up by 1 each time, right? So what we're going to do is this, is we're going to figure out what degree this function is going to be by using finite differences. This is how this works. What we do, kids, is this. We go -4 minus -2. Okay, what is -4 minus -2? Oh, I want to think. Hang on a second. I'm doing this the wrong way. We got to go the other way. We should do -2 minus -4. In other words, to go from -4 to -2, you would move up by how much? Okay, there'd be a change in y of 2, okay? Now, how about the next one? To go from -2 to -4, what's that change? Wouldn't that be -2? Just do -4 minus -2. So always this one minus the previous one. So this one was -2 minus -4. When you subtract -4, it's like adding 4, right? What's -4 plus 2 really then? Isn't that -2? Okay, it goes -16 minus -4. Negative how much? Yep, this would be a -12. Okay, somebody do this one for me. -44 minus -16. Okay, I should get -28 for that, I believe. Somebody do the -94 minus -44, or in other words, -94 plus 44. What would that be? And then right here, do -172 minus -94. And think about it. If it was 94 below 0 to 172 below 0, is that getting bigger or smaller? Okay, so it's going to be a negative number. What is -172 minus -94? -78, okay? Now kids, we said, hey, the x's are all jumping by the same amount. When I look at these differences in y's the first time, are those differences exactly the same or are they different? They're different. So what we do is we say, okay, let's go through them again. So here, we're going to do -2 minus how much again? 2. What is -2 minus 2? -4, right? Somebody do -12 minus -2 here. Should be -10, shouldn't it? -28 minus -12 would be -16. Whoops. -50 minus -28 is -22. -78 minus -50 is -28. How many times have I looked at differences, kids? How many rows of differences? We've looked at 2. In that second row, are they exactly the same? No. So what we do is we say, okay, let's do it for a third time. And check out what happens here in the third. Kids, what's -10 minus -4, or -10 plus 4 in other words? -6. Ooh, what's -16 plus 10? Or what's the change here again? Ah, I see something. What's the change here? What's the change here? It's negative what? Ooh, doggies. What happened right here, kids? They're the same, okay? How many times do we have to go through it before we got the same finite difference? 3 times, okay? This means that this is a third degree function. Okay, now here's the deal, kids. They want us to come up with an equation for that, of a third degree function, okay? And here's how this is going to work, all right? For this third degree function, this is what you're going to type into Desmos. You're going to type in y1 is approximately a x1 to the, what degree do I want first? Well, what degree did we say this was? So we're going to call this ax1 to the third plus, let's see, I already used a, so my next term probably might want to use what? B x1 to the, well, if we started with a third, the next term below that for polynomial functions would be a second degree function plus maybe cx1 to the first plus your constant out here that I'm probably going to call what, kids? D. Okay? Here's how this works to come up with a function for this. Okay? First of all, do you guys understand why this is a third degree function? The x is all jumped up by 1. So what we started doing was looking at differences. First row of differences, not the same. So we go to a second row of differences, not the same. But we went to the third row, and what happened?
They're the same.
Differences were the same, which means that this has to be what type of function, or what degree?
Third degree function.
Okay, so here's how we come up with the function. Let's jump into Desmos. You guys are going to need to read these values for me, all right? So here's how this works. Let me jump into Desmos for me quick. Maximize, whoops, what did I do? I want this. Okay, if you guys recall, when we do this here, we need to first of all make sure we put in a table. So up here you have this little plus sign, and we're going to put a table in up here, okay? So I need the values to plug in. I'm going to go over to my computer here. So tell me what the values are. 1 comma what first, kids?
Comma, -4,
Next point.
2, comma, -2,
Next one.
3, comma, -4,
-4? I'm listening.
4, comma, -16,
Whoops, I didn't want 165, did I? All right, 5 comma.
-44,
6 comma.
-94, 7, comma, -172.
Okay. Are you guys okay with putting the table in there like so first? Okay. So guys, first of all, what function do we come up with? What degree did we get? Okay. When we type these in, here's what we do now, kids. To come up, and this is the technology piece that we're talking about. How do I write an equation of degree 3 to model this data? Well, it becomes y1 like so. I have to type y1 because these values y up here are listed as y1. All right? Then the next thing you need to do is put in that little squiggle mark. Everybody know what squiggle mark I'm talking about? Because we've done this before with quadratics. You guys all know what I'm talking about? Okay, and then we said a x1 to what power, kids? Okay, so I'm going to raise this to the third. What was next? bx, and I always have to put the little 1 bx to the plus what? cx1 down there, don't all, and then plus what finally, kids? Gosh, kids, check this out. First of all, some of those points plotted right there for us. Okay? How many turning points to this graph, kids? 2, which meant degree 3. Oh my lord. Do they give me an A value right here? Do they give you a B value? Do they give you a C value? And do they give you a D value? So on your notes, I'm just going to go ahead and take a picture of this real quickly, but in your notes there to write the equation, I'm just simply going to say, well, this becomes the following. It becomes y equals, all right, we had what, ax1 to the third, was that right? Well, what is the a value according to this when I plug all that information in? So it becomes -1x to the third, and then bx squared, so plus what? Plus 4x to the second, plus cx, which would be minus 3x, and then minus 4. There it is right there, kids. Quick question here in terms of using technology. Do you understand how to put the table in? That's my first part. Then the second part is, you just keep starting with ax1 and you go all the way down until you get down to the third power, second power, first power, and then a constant. If I had like a 7th power, this would end with some other letter than D. You just keep moving your alphabet up. All right? So let's look at the last one together. Everybody get that function down on example, whatever was that? Was it 2?
Yes.
Okay, all right, so let's take a look then at our next part right here. This last part on this last page. It's the same thing, kids. It's the same thing. Modeling real life situations. Okay, it says the table shows a person's billable hourly fee in dollars in the last year T, where T equals what, kids?
1.
T equal 1 corresponds to what year? I'm just going to jot this down. 2005. That's that year right there. Okay, it says find the polynomial model for the data, and then use that model to estimate the fee in 2012. Okay. They're saying, hey, put this information in, come up with a function, and then use that function to model what the value of the billable fee will be in 2012. Okay, so help me put the points in. Let me get back to Desmos. Okay. All right, so let me clean this stuff up. All right, by Desmos, first of all, what are my points? 1 tab 20.
2, 21. 3, 15. 4, 13.
5, 23.
6, 53.
653?
Yeah.
Okay, now my question is this. I don't know what degree this is. So I don't even know where to start with for degree. So we better figure that out first. We have those points in there. Some may show up. I'm going to zoom out a bit so we can see some of these points. Okay, we see a few of them. It's kind of a mess right in there. We better figure this out, kids. What's the difference here? 21 minus 20. 1. 15 minus 21. Negative 6. And 30, right? Are they the same or different? Okay, let's do negative 6 minus 1. What is that, kids? Let's do negative 2 minus negative 6. So that would be positive 4. How about 10 minus negative 2? Wouldn't that be 12? This minus this, what is that going to be? 30 minus 10 would be 20, right? I don't know, do I have my numbers right up there, guys? Looks like I do. Gosh, did I put those numbers in? Hang on one second, kids. 20, 21, 15, 13, 23, 53. What are you saying here, kiddo?
Oh, never mind. I found it.
Am I okay there? Ooh, I'm not liking this for some reason. Something's wrong.
Few win time announcements. Reminder that there is win time today. Freshman study hall win time will go to the auditorium. Sophomores, the library. Juniors, the cafeteria, and the seniors, the auditorium. For study hall win time, freshman auditorium, sophomores library, juniors cafeteria, and seniors auditorium. Also, if you signed up for Mr. Boston's win time today, you will go to the upper gym.